everybody. This tutorial is going to give you some help on how to navigate the mathematics that are involved with a circuit that has a resistor and an inductor. It's going to be very important for you to have a calculator handy so you can work out the problem with me, so you can get some practice on how to solve for these variables. Okay? So here we have a combination circuit with one resistor and one inductor. The resistor has a value of 60 ohms and the inductor has an inductance of 5 henries. We have a 120 volt source at a 60 hertz frequency. Alright, in order to solve for this, for all the parameters in this circuit, the first thing you need to see and recognize is the fact that the inductor has a value in henries while the resistor has a value in ohms. There's no way that you can possibly combine these two until the inductor is changed into an ohmic value. The only way that you can change the inductance into a ohmic value is using this formula, which is the inductance reactance is equal to 2 pi times the frequency of the circuit times the inductance of the inductor. Okay, so basically all you have to do is replace the values into that formula. So we have the frequency, it's right here, 60 hertz. Remember that hertz always gives you the clue that it's a frequency. And here we have the henries, which is the inductance. So you take these two values and you replace them into this formula. So let's do that. So I have the inductance reactance equals to 2 pi times the frequency, which is 60 hertz, times the inductance, which was 5 henries. Alright, so now all you got to do, and go ahead and do it with me, alright, so you can get some practice. It's 2 pi times the 60 hertz times the 5 henries, and I get a value of 1,884.95 ohms. So, as you can see, the Henry value that you got from the inductor has been changed into an ohmic value. And that is the first step that you need to do to solve this circuit. To change the Henry value into an ohmic value. And once you have the ohmic value, this will make the next calculation much easier. So as you can see, we have changed the Henry value into an ohmic value for the inductor. So we go back to my circuit and I replace the Henry value, the inductor's value, for an ohmic value for the inductor. So now as you can see, I have ohms for the resistor and I have ohms for the inductor reactance. Okay? Now these two can be combined to get the overall resistance for the circuit. However, because this is not a resistor, but it's an inductor, you cannot just add the ohmic values, 60 plus 1,884.95. You do not add them that way. In order to add a resistor to an inductor, you use this formula. And the result you're going to get is called the impedance. And of course, the impedance has the letter Z for it. So let's go ahead and replace our values. The ohmic value for the resistor was 60 ohms, so I'm going to replace it. 60 ohms squared plus the inductance reactance for the inductor, which is 1884.95. Don't forget to square it. Alright, so now you just need to calculate this. Use your calculator. You take the square root of 60 squared plus 1884.95 squared, and I get 1885.90 ohms. Now, one thing that you need to notice is how, even though I have a 60 and an 1884, it did not add linearly. I didn't get 1884 plus 60. It's barely 1885.90. And that's because of the way that we use this addition for the impedance. But now you see that it has an ohmic value, and this ohmic value is for the entire circuit, right? So do not get confused between the impedance and the inductance reactance. They're all ohmic values. It's all added forward resistance. But this will help us calculate the total current in the circuit, as we see next. Okay, so now that we have calculated the total impedance for the circuit, right, I can put it down on my circuit, and here we go. The total impedance, which is the resistance in the total circuit, including the inductor and the resistor, is 1885.90 ohms. Now that I have the total resistance in the circuit, which we call impedance, I can calculate for the total current. So in order to calculate the total current, I'm just going to take you back a little bit through Ohm's law. Remember that in Ohm's law, when we did DC, it was voltage equals the current times the overall resistance of the circuit. But because now we have an inductor, they changed the total resistance into impedance. But don't get confused. It's still an ohmic value. It's just that now it has the fancy name of impedance because it has an inductor in it. But let's go through the calculation anyway, and you'll see that it's the same thing. Since we're solving for current, all we need to do is reformulate this, and it turns into the voltage divided by the total resistance gives me my total current. Well, that's the same thing you do over there. The voltage divided by your impedance gives you the total current. So as you can see, there's nothing different. It's just different names for the overall resistance in the circuit. So now let's go get our values. We go back to the circuit, and here we have the voltage for the entire circuit, which is 120 volts. So let me replace that. 120 volts. And now I need my impedance, which was 1885.90. So I'm going to substitute that. And as you can see, it's a very simple division. So let's get our handy dandy calculator. And 1885.90. And I get a current of 0.063 amps. Okay, and this is the total current for my circuit. So the most important thing here is do not get confused with the fact that now we have a Z for impedance. It's still resistance for the circuit, and it has an ohmic value, as you can see. Now we have the total current for the circuit, and this will help us further on for all the other calculations that we need to make. So these are all the values that we've calculated for the circuit thus far. Okay, we changed the inductance value into an ohmic value for the inductor. Then we used the ohmic value for the inductor and the ohmic value for the resistor to get our impedance. And once we obtained the impedance, we used the impedance to get the total current for the circuit. Now that we have the total current for the circuit, we can do other things like calculate power. Now, this triangle is very important because the titles for each segment of the triangle are important for you to remember. The hypotenuse of the right triangle is called the apparent power, and that's the total power of the circuit. It's very important that you always keep it on the hypotenuse side. The reactive power is the power that comes from the inductor, and that always goes on the vertical line. And the true power is the power that comes from the resistor, and that always goes on the horizontal line. It's very important for you to keep track of where all these labels go on the triangle. You cannot switch the labels or your math is going to come out wrong in later calculations. All right? So we're going to go and calculate the true power, which is the power of, like I said, the resistor. And the power formula we're going to use is the power equals to the current square times the resistance of the resistor. All right? So let's go back and get our values. We know that the total current is 0.063 amps. So let me replace that. 0.063 amps, and we're squaring this, times the resistance of the resistor. Okay, so it's 60 ohms. So I'm going to replace that. This will give me my true power, which is the power of the resistor. So you put these values into the calculator and you get 0.063 squared times 60 ohms, and I get a value of 0.238 watts. Remember that the unit for power is watts. So this is my value for true power. So now you go to your power triangle, and this is where it goes. That is my true power for the circuit. So as you can see, we have calculated now true power, which is the power that comes from the resistor, and we calculated it to be 0.238 watts. The next step is for us to calculate the reactive power. And of course, the reactive power comes from the inductor. And that's also very key for you to remember where these powers come from. Now that I know that the reactive power comes from the inductor, I use my power formula again, and I just substitute the values. So we go back to our current again. We're going to square the current to get our current value is 0.063 amps. So 0.063 amps squared, and you're going to now multiply it by the resistance of the inductor. But remember, the resistance of the inductor had a special name. It's the inductance reactance. Okay, so it's this value right here, 1884.95 ohms. Even if you don't recognize the title of the value, you should recognize the units since we're doing the ohmic value. So it's 1884.95 ohms. And you replace that over here. 1885.90 ohms. Okay. Now you just put this value, all these values into your calculator. 0.063 amps squared times 1885.90, and I get 7.48 watts. So this is the reactive power that comes from the inductor. And now that I have the value, I can just replace it right here. 7.48 watts. So now I have my reactive power and I have my true power. The next thing that we're going to calculate is the apparent power. So as you can see, we have calculated now the true power, which we got at 0.238 watts, and we just finished calculating the reactive power at 7.48 watts. The last step for our power triangle is to calculate the apparent power. And if you recall, the apparent power is the total power of the circuit. So because it's the total power of the circuit, we need the total current of the circuit, which we're going to be using, but we're going to use the impedance of the circuit, which is the overall resistance in the circuit, to get the total power. Again, don't get confused by the fact that I used the letter Z. It's still the resistance, but because there's an inductor, we have to use the impedance for Z. So let's do that and get some values. We have the current again. The total current is 0.063 amps. Don't forget to square it. and you're going to multiply times the impedance. And this time we use the impedance, and make sure you don't use the inductive reactance. We're using the impedance, and it's 1885.90. All right, so let's get our handy dandy calculator and see what we get. We have 0.063 square times 1885.90, and I get 7.485 watts. This is the value of my apparent power, which I can now substitute into my triangle. So now I have all three values, the value for the apparent power, the value for the true power, and the value for the reactive power. One thing you will notice is like, oh, wait a minute, look, the reactive power is almost the same as my apparent power. That's kind of weird, right? Well, the only reason it's kind of weird is because remember, these things do not add linearly. You're not doing 7.48 plus this. You add it using the Pythagorean theorem, which we're going to show you next, how to check to see if your values are correct. Okay, so now we've calculated the three types of power that you're going to get in your circuit. Remember, once again, the true power always comes from the resistor, and it's always on the horizontal line of your triangle. The reactive power always comes from the inductor, and it's always on the vertical line of the triangle. And the apparent power is the overall power in the circuit, and it's always the hypotenuse of your triangle. So these are the values that we calculated for those three. The last calculation that we do is the power factor. And the power factor gives you an idea of how efficient your circuit is. So of course you want a high power factor. So let's calculate that. In order to calculate the power factor, you get the resistance of your resistor, and you divide it by the impedance of the overall circuit. And once you get that fraction, you just multiply by 100, and that gives you a percentage. So let's do that. If you get the resistance for the resistor, let's go back, it's 60 ohms. And the impedance is 1885.90. And all of that multiplied by 100. So let's see what we get. 60 divided by 1885.90 times 100. So if you got the number that I got, which is 3.18%, this circuit is not very good. Obviously, it's not very efficient. At 3.18, the power factor is not very good. You want something that's up in the upper 90s in terms of percentage. So 3% actually is not very good. Another way that you can get your power factor is to go back to your power values. And you do the same thing. You get the power for the resistor. Excuse me. The power for the resistor is 0.238 over the overall power, 7.485, and then you multiply that times 100. Let's see if we get the same thing. So 0.238 divided by 7.485 times 100. And lo and behold, I get 3.17%. So as you can see, there's different ways in which you can get the power factor for your circuit. If you have all the power values, then you can use the power combination, the power from the resistor divided by the overall power of the circuit gives you the same percentage than if you use the resistance of the resistor over the impedance of the entire thing. You get the same, almost the same value, 3.18%. Okay? This is basically all the calculations that you need to make for your combination circuit that deals with a resistor and an inductor in series. On the next lessons, we'll discuss a resistor with a capacitor, and the mathematics are very similar.